This talk is on data oblivious algorithms for multicores, and this is joint work with Elaine. So there is a lot of need for privacy of data, and that is needed in many applications. And this talk deals with maintaining privacy of data during a computation. The common way of maintaining privacy of data is to encrypt the data. And this preserves privacy during the storage of data or transmission of data. But there is still leakage of information during a computation just based on the data access pattern. And a data oblivious algorithm is one where the data access pattern reveals no or negligible information about the actual data. And this concept was first introduced by Goldberg-Ostrovsky in 1996 and has been refined in many ways since then. And I will talk about the design of efficient data oblivious algorithms for multicores. Now, there are two main design techniques for data oblivious algorithms. Now, for deterministic algorithms, we need an algorithm to have a data access pattern that depends only on the size of the input and not on the values in the elements. And that will give a data oblivious algorithm. And we have many common examples. The standard algorithms for prefix sums, matrix multiplication or FFT, or Boolean or comparator circuits. So in all of these cases, once you fix the size of the input, the data access pattern is completely fixed. You can also have randomized data oblivious algorithm. And here we require that the memory access pattern has the same statistics for all inputs of a given size to within what's called a negligible probability of failure. And a negligible probability of failure is a probability that is smaller than 1 over any polynomial in the input size. So it is it's a stronger requirement than what's required with high probability. And there are various versions of data oblivious algorithms, and we make some pretty strong assumptions. For example, we will be looking at cache efficiency, but we are secure against data leaks through cache access timing. So our data obliviousness extends to computations in the cache. And our algorithms are secure against computationally unbounded adversaries. That is, we don't assume that the adversary is, say, polynomially bounded in the amount of effort it can extend. And in cryptography terminology, this means that we achieve statistical security. So that is for the data oblivious part of our work. The multi-threaded model that we use is a CREW binary fork join algorithm where the forks and joins are paired. So this gives rise to a series parallel computation DAG. And we assume a shared memory machine with P processors. We will consider caching costs. So we assume each processor has its own private cache. The performance measures we consider are the work, which is simply the sequential running time of the algorithm, of the multi-threaded algorithm, if it is executed on a single processor, and the span T infinity, which is its parallel running time, or the length of a longest path in the computational DAG. So we also consider caching complexity. So the caching cost is going to be the number of cache misses incurred in a sequential execution, as is the commonly used in this framework. And that's because the parallel caching complexity will depend on the scheduler used, and the sequential caching complexity can then be translated into, good bounds for a scheduler, for several well-known schedulers such as randomized work stealing. So we'll use the cache oblivious model of Frigo et al. But we will call it the cache agnostic cost instead of cache oblivious, because we will use oblivious for data obliviousness. We'll assume the cache size is M and that it is partitioned into blocks of size B. So our multi-threaded model is, paired binary fork joins and CREW, and this allows for well-structured algorithms. We do not use atomic operations or concurrent writes in our algorithms. And for our caching bounds, we assume that the cache size M is omega block size B to the 1 plus epsilon for some epsilon greater than 0. This is called the tall cache, and this is in fact required if we want an optimal sorting bound. We also assume that the cache size M is omega log to the 1 plus epsilon of N for some epsilon greater than 0. So it's at least logarithmic or slightly more than logarithmic in the input size. So here our main result is for sorting, asymptotic result is for sorting, and here we present butterfly sort, which is a data oblivious sorting algorithm, whose bounds match the current best algorithm, which is of course not data oblivious, it's insecure, on the CREW fork join model, and that is the SPMS sorting algorithm, sample partition merge sort. And so we achieve optimal work and cache agnostic caching costs. And we are a log n factor off of optimal for span, at least the known lower bound for span, log n, matching SPMS. Now, if we compare ourselves to prior data oblivious, we do very well because even sequentially, no data oblivious algorithm was known that achieved both work and cache optimality, even in the cache aware setting. And we get work and sorting optimality plus close to optimal span. So I've listed a couple of bounds. AKS, the sorting network, achieves optimal work, but it's way off in caching complexity, and its span is also larger than ours. And Chan et al. Achieve cache oblivious, cache agnostic optimal caching cost, but they don't get optimal work, and their span is pretty large. So now, in addition to butterfly sort, we apply butterfly sort to get many other, together with other data oblivious algorithms to get several other results, including a CRCW PRAM step simulation on the CREW fork join. And for linear space-bounded CRCW PRAM computations, which is what a vast majority of results are, we can simulate with the same bounds as the sort bound. And using this result, we are able to get data oblivious algorithms for many problems, such as tree contraction, graph-connected components, minimum spanning forest. And in all of these cases, we actually improve the span over previous insecure methods, because previous methods did not use go this simulation route. And we also match previous bounds for other problems like list ranking and Euler-Tour. And we have other results which you can see in the paper. So now I will move on to our butterfly sort and some more practical versions. So butterfly sort is based on an earlier data oblivious sorting algorithm, sequential one, which is called bucket oblivious sort. And it has a simple structure, and so does butterfly sort, since it follows the same structure. So for this, we construct a random permutation of the given input elements, unsorted input elements, and we do this in a data oblivious way. That is the key step, because Asheroff et al. Show that once you've done this, you can sort the randomly permuted array with any sorting algorithm. It need not be data oblivious. So we, for instance, can use SPMS for step 2. So now coming to random permutation construction, there again, it's in 2 steps. we first create a coarse random permutation by moving each input element to a random bin. And then in the second step, we create a random permutation within each bin, the elements of each bin, and we concatenate the bins. And it turns out that once we do step 1, step 2 is pretty easy to do. So we will concentrate on step 1. That's our key contribution. And for step 1, we have a method for oblivious random bin assignment, which we call ORBA. So the bins are going to have size theta of log squared n. Log 1 plus epsilon will also work, but log squared n for simplicity. And we create a sequence of output bins, beta of them. Beta is going to be n over z, and each of size z. And each input element is given a random label between 0 and beta minus 1. And our task is to obliviously move each input element to the bin numbered by its random label. So oblivious. And the way we are going to do that is we'll route them obliviously using a butterfly network, but suitably enhanced to preserve obliviousness. So this is going to be our structure of our algorithm. The inputs are at level 0, partitioned into these bins of size theta of log squared n, z, and they will be routed along this butterfly to the output bins, to the corresponding output bins. And of course, we can't use the butterfly as is because that would not be oblivious. Instead, we put a distributor at each between pairs of inputs and their corresponding outputs. And this distributor needs to be oblivious, needs to obliviously move the elements from input bins to the corresponding outputs, which are inputs at the next level. So this is the structure of our ORBA algorithm. The question is, what is the oblivious method for the distributor? We are going to use the AKS sorting network. Now, these are small-sized AKS sorting network. And together, we do need to add a few additional features to ensure data obliviousness. I won't go into those here. But even with AKS, this increases the work per level to n, super linear. And so we won't get an O of n log n oblivious binning scheme. So to account for this, we won't use the exact butterfly. Instead, we'll merge log n levels of the butterfly. And then we would only have log n over log n levels. And then we can, in fact, use an AKS sorter because it will only take, across all the sorters in a level, we'll only spend n log n work. And with log n over log n layers, we will get an n log n method. And that's, in fact, our algorithm for oblivious random bin assignment, our base algorithm, which we call MetaOrba. And so it's readily seen, as I just mentioned, that in each, a single distributor takes time, log cubed n, because that's the total number of elements that it sorts. There are log n bins, each with theta log squared n elements. So log cubed n log n work. And if we just stay with EREWPRAM, it's O of log n time for the parallel time. And so MetaOrba takes n log n, optimal n log n work. And on an EREWPRAM, it also gets optimal log n time. But of course, we can also get this with a single large AKS network. Now, to get our binary fork join algorithm, we use the same strategy that is inspired by getting good binary fork join butterfly. So we group the bins into square root of n groups of square root of n bins each and solve recursively. And that takes care of the top half of the layers. And then a suitable matrix transposition will rearrange the bins so that they are in the same configuration as the start of the first layer, call for the second call down here. And so once we complete the second layer, we are done and we get the oblivious random bin assignment. So we start with beta bins, and so the recurrence for the caching cost is given with the Q of Y, and the recurrence for the span is given with T of Y. Now for the base case occurs when you are with a single distributor and the cost is dominated by the AKS computation. But now the base case fits in cache. So the caching cost is just a span bound and the scan bound. And the span, base case span is, if it was ER-EW, it would be log n span, but then we have to do it in binary fork join, so we get an additional log n factor for forking and joining at each level. So these are the base cases, and if you solve the recurrence with this base cases, we get exactly what we had promised earlier: optimal caching, cache oblivious caching cost, optimal work, and a span of log n on binary fork join CREW. In fact, this is EREW because there was no CREW here. The overall sorting algorithm, butterfly sort, is CREW because it uses SPMS, which is a CREW algorithm. Now, I'll just spend a couple of minutes about our simplified sorting variant. So butterfly sort is our asymptotically, good data oblivious sorting algorithm. However, it's fairly complex. I mean, of course, it uses small AKS networks, but also it uses SPMS, which is quite involved. Now, we get simpler versions for which we first start with observing that we can get a fairly good bitonic sort for binary fork join by observing that the bitonic merge within bitonic sort is itself a butterfly. So we can exploit the good layout for butterfly. And so, of course, the work remains n log squared n as with basic bitonic sort, but the span instead of log cubed n can be reduced to log squared n log n. And the caching cost can be the sorting bound times log n over n. Now, our sorting, here it is. So for our sorting variant, what we will do is a simpler version of sorting. Instead of SPMS, we observe that we are using the full power of SPMS to sort a randomly permuted array. Instead, we'll use a simpler algorithm for the randomly permuted, sorting the randomly permuted array. And we call this butterfly random sort because it's going to be very similar to our RecOrba, which we just saw. And the only difference is going to be that the buckets will be, the sizes of the buckets or the contents of the buckets will be determined by a sorted set of random pivots. Now, the sorting of the random pivots will be done with our improved bitonic sort. And then we just do a repeat of what we did for RecOrba to get the elements into their sorted positions in bins. And then we sort within the bins to complete the sorting. And that gives us two algorithms which essentially use the same approach, but one version, which we say potentially practical, uses bitonic sort everywhere. So the entire algorithm just uses bitonic sort and prefix sums. It has optimal caching cost. The work is off by a log n factor, and the span is increased by a log n factor over butterfly sort, but the constants are very small because it just uses bitonic sorts and prefix sums. So we consider it to be potentially practical. And of course, it's EREW. And our second EREW version has optimal work and caching complexity. It's just the span that is increased by a log n factor. And here the difference is for the small problems, instead of using bitonic sort, we use either AKS, or we can even use zigzag sort by tweaking the parameters a bit. And so that is an EREW version, and it also has optimal work and caching cost. So I will stop here and wrap up to observe that we have presented efficient data oblivious algorithms for many fundamental problems on the CREW binary fork join algorithm model, finally. And for all problems, we match or improve on the prior insecure results. And all caching results are cache agnostic. And our central result is butterfly sort, which even improves on data oblivious algorithms in the sequential case when if you want cache efficiency. And we also match the current best performance of our binary fork join sorting. And in fact, our data oblivious sorting, just using our MetaOrba, which is what we presented, can be adapted to match the best results for sorting in other models like the BSP and the parallel external memory.